Hi everybody, my name is Rune Fiedler. I will convince you that there is more to signatures than just unforgeability, how you can buff your signature schemes beyond unforgeability, and what this means for post-quantum signatures. This is joint work with Cas Kremas, Samet Düzlü, Mark Fischlin, and Christian Jansson.
So you may have heard of signatures before. Signatures have plenty of applications. You can use them to sign messages, to authenticate software updates, and as a building block for bigger protocols such as a key exchange protocol. All in all, they are a fairly important cryptographic primitive. The security notion that signatures are usually measured against is called existential unforgeability. An attacker against existential unforgeability has to output a forgery for a fresh message. This security definition has stood the test of time for several decades, hence it is also used for the NIST competition on post-quantum cryptography. However, this definition is only concerned with honestly generated public keys. But what about maliciously generated public keys? In this presentation I will tackle 4 questions. Can maliciously generated public keys actually break real-world protocols? How can we formalize the notions of maliciously generated public keys? And once we formalize the attacker model, how can we achieve security against maliciously generated public keys? And lastly, do the NIST finalists actually achieve security against maliciously generated public keys? Then let's have a look at a real-world protocol. This is about Let's Encrypt. Let's Encrypt is a certificate authority from which you can get a certificate for your website. In order to get a certificate, you need to convince Let's Encrypt that you are the rightful owner of the website. And this can be done with the following protocol. It begins with the owner of the website who has a key pair and tells Let's Encrypt that he would like to register his website. Let's Encrypt will generate a challenge token and send it back to the owner. The attacker will then use his secret key to generate a signature on the challenge token. And then the owner will update the DNS record for his website, such that if you query this website, you will get the signature as a return value. And next, Let's Encrypt will precisely query this DNS record to get the signature. And this DNS record can only be changed by the rightful owner of the website. That is how Let's Encrypt is convinced if the signature actually verifies, which is what Let's Encrypt checks in the next step. And if the signature verifies the challenge token that Let's Encrypt issued in the beginning, Let's Encrypt is convinced and issues a certificate to the owner. Now this is how an honest execution of the protocol looks like. We are in the setting that an honest execution has taken place, and now an attacker enters the stage. The attacker wants to get a certificate for the very same website, and starts another execution of the protocol with Let's Encrypt. Let's Encrypt will then, however, generate a new challenge token and send it to the attacker. The attacker somehow finds a new public key. Let's not concern ourselves with how it does this, but it finds a new public key such that the previous signature verifies this new challenge token. Then it tells Let's Encrypt, oh, by the way, I got a new public key, just so you know. Next, Let's Encrypt will once more query the DNS record for this website and get the same signature as before, which was honestly generated. Now Let's Encrypt will check if this signature, which was honestly generated in the previous protocol execution, verifies the new challenge token under the new public key. And since it does, it accepts and issues a certificate for the attacker. At this point there are 2 problems. First, now the attacker has a certificate for a website which it does not own. And second, something strange happened with the signature scheme. It didn't break existential unforgeability, but something happened that intuitively should not have happened. How can we formalize what we have just seen to get a definition for this type of maliciously generated public key? Let's think about what just happened. there is a honestly generated public key and a message, and then there's an honestly generated signature that verifies this message under the honestly generated public key. And all three of these values are known to the attacker. And the attacker then produces a new public key, such that the old signature, the original signature, verifies a different message under this new public key. And that is a flavor of exclusive ownership. More specifically, this flavor is called strong destructive exclusive ownership. You can find out more about the other flavors of exclusive ownership in our paper. And there's two more notions of security against maliciously generated public keys. The first one is called message-bound signatures, which deals with whether a signature is bound to a message. So an attacker against message-bound signatures has to output a public key, two messages, and a signature, such that the signature verifies either message under this public key. And the third notion is called non-resignability. Here we once more start with an honestly generated public key, some message, and an honestly generated signature on this message. The attacker will then get the key and the signature, but not the message. And the attacker is required to output a new public key and a signature, such that the signature verifies the message, which the attacker does not know, under the new public key. All of these security notions in combination are what we call the beyond unforgeability features. So that is the flavors of exclusive ownership, message-bound signatures, and non-resignability. All of these notions are independent of each other, and the proofs for that you can find in the paper. So how can we achieve security against these maliciously generated public keys? Of course, for any specific signature scheme, you can try to find a proof specific for this scheme. For some schemes this may be easy and has been done already, and for other schemes this is infeasible. And specifically for the second case, we are proud to present the buff transformation, which achieves security against all beyond unforgeability features. How does this work? We start off with a signature scheme that does not yet provide the beyond unforgeability features and a hash function. The key generation algorithm stays the same. However, we have to apply some modifications to the signing algorithm. First, we compute the hash of the public key and the message. Then we sign this digest with the signing algorithm of the original scheme. That is, we just plug in the digest instead of the message. Then the signing algorithm returns the digest and the signature. So a signature of the modified scheme has a modest size increase of 1 hash digest. The verification algorithm also needs to be changed accordingly. First, we check that the hash digest that is included in the signature matches the hash of the public key and the message. Then we invoke the verification algorithm of the original scheme with the hash digest as message. If both conditions hold, the signature is accepted. As you can see, the overhead in terms of computation time is a hash function evaluation in both the signing and verification algorithm, which is usually negligible. The security of the buff transformation reduces to security properties of the hash function. The crucial point here is the extra step in the verification algorithm, where we check the digest in the signature. This ensures that a signature is bound to one public key message pair. A successful attacker against exclusive ownership or message-bound signatures produces a signature that verifies under several public keys or for several messages. If a signature verifies with 2 public key message pairs, then both public key message pairs need to have the same digest in order for the verification algorithm to accept. Hence, an attacker produces a collision in the hash function. The security argument for non-resignability is slightly more involved, so I leave it for you to find in the paper. So, as we've just seen, it's quite doable to achieve these security notions. And let's dive into the NIST finalists. Do they actually achieve security against maliciously generated public keys?
We have analyzed the signature schemes as they were submitted to round 3 of the NIST competition. As you can see in this table, some do, some don't.
A tick means that the security property is achieved, so Dilithium and Picnic achieve all the security notions. And an X means that we have found and given an attack, which you can find in the full paper. So Falcon and Rainbow are so-so, while Gems has a lot of potential for improvement. As for Sphinx Plus, we couldn't give attacks or proofs for exclusive ownership and non-resignability. So with this you might say, okay, how can I achieve all of these security notions? Didn't you just introduce some cool transformation? Yes, you are right. You can straight apply our buff transformation to achieve all of these security notions. And another advantage, the signature size hardly increases. Specifically, the relative signature sizes stay the same. So for Falcon, you may want to apply the buff transformation to achieve all the security notions. However, after applying the buff transformation, Falcon signatures are still shorter than Dilithium signatures. So what have we seen in the last couple of minutes? We have seen that maliciously generated public keys can be a serious problem to real-world protocols. We have seen that there are several types of maliciously generated public keys, and we call the combination of all these security notions beyond unforgeability features. Then we introduce a generic transformation to achieve all of the beyond unforgeability features, which is quite efficient and has a modest increase in signature size only. Lastly, we looked at the NIST finalists and saw that not all of them achieve the security guarantees, which are nowadays already quite easy to achieve. If you're interested, please have a look at our full paper, which you can find on ePrint, and I'll be happy to take any questions.